All right, so here we go, here we go. It's another one of those videos. Students better recognize that I'm teaching and I'm finna make it known that I'm still want to call each and every one of y'all out. Let's see who's learning and who's not when it comes to the math. I'm gonna bring it to you live and in this video. So let's get to it. Well, what exactly is this video, you might be asking? That's a great question. If you didn't figure it out from the title on the screen, it is using trig derivatives. So what we're gonna be doing is, you guessed it, using trig derivatives. The good news is you already know your trig derivatives. So most of this is really just going to be practice. Yeah, we're talking about practice. That's what we're going to be doing here. So with that, let's go ahead and jump into it. So with this problem, we want to find the tangent line or the equation of the tangent line in slope-intercept form for f of x equals x tan x at pi fourths. This is something we should know how to do. As I just mentioned a minute ago, or not a minute ago, a few seconds ago, I'm going to have you try these on your own. I want you to get the practice, spread your wings a little bit, fly, explore. So yeah, pause the video, find the equation of the tangent line at x equals pi fourths for f of x equals x tan x. In slope-intercept form. I want exact values for this as well. Go ahead, pause the video, and unpause when you are ready to check your work. Okay, so we should see that we get y equals the quantity 1 plus pi halves x, so our slope is 1 plus pi halves, minus pi squared over 8. So that is our slope-intercept form. Let's look and see how do we get that. Well, the first thing I did was I found the y coordinate when x is pi fourths. So if I plug pi fourths into the function, I get pi fourths tan pi fourths. Tan of pi fourths is 1, so pi fourths times 1 is pi fourths. Great. So now we know the point pi fourths comma pi fourths is on our function. Now, in order to write the equation of a line, we want a point and we want a slope, and then we can write our slope-intercept form. So to find the slope, we need to do the derivative. To do the derivative, we need to do the product rule. So I did the derivative of the first times the second plus the first times the derivative of the second. So here is the derivative of the first times the second plus the first times the derivative of the second. Now I am going to go ahead and evaluate the derivative at pi fourths. Remember, the derivative represents the slope of the function at every x value. We want to know what is the slope when x is pi fourths. So I plug in pi fourths. The tangent of pi fourths is 1. We got that. And then this becomes pi fourths times the secant of pi fourths, quantity squared. The secant of pi fourths is root 2. Root 2 squared is 2. 2 times pi fourths gives us the pi halves. So then our slope of the function when x is pi fourths is 1 plus pi halves. Now, moving on to my slope-intercept form, y equals mx plus b, plug in the point and the slope and solve for our b value. So I can plug in the point, pi fourths. I can plug in my slope, do a little bit of arithmetic. I get these great numbers. I end up with b equals negative pi squared over 8. And then I rewrite my slope-intercept form. Any questions? Okay, great. Moving on. Let's do the next one. So given f of x equals cosine cubed of x, find the critical values for x in the interval 0 to 2 pi. So notice here, all we're doing is finding our critical values. We are not doing anything with the critical values, just finding the critical values. Also, can anyone tell me why do we have the interval 0 to 2 pi? Anyone? Come on. All right, you're being a little shy. That's fine. So remember, we want the interval 0 to 2 pi because technically there's going to be an infinite amount of critical values. So having the interval 0 to 2 pi is just going to limit that so that we don't have to write the infinite amount. So again, I want you to go ahead and try this on your own. Find the critical values, pause the video, unpause when you are ready to check. Okay, so my critical values, I got x equals 0, pi, pi halves, and 3 pi halves. That is in the interval 0 to 2 pi, including the 0, not including the 2 pi. How did I get that? Great question. Glad you asked. So First thing, find the derivative. This is cosine cubed of x, so we need to do the chain rule. So I bring down the 3, this becomes cosine squared x times the derivative of the inside. What's the derivative of cosine of x? It's negative sine of x. Find critical values, set that equal to 0. Great. Now this is nicely factored for us, so I can just go ahead and set each of the individual factors equal to 0. Here, divide by 3, take the square root. The square root of 0 is plus or minus 0, which is just 0. So where does cosine equal 0, and where does, in this case, sine of x equal 0? Sine of x is going to equal 0 at 0 and pi. Cosine equals 0 at pi halves and 3 pi halves. Great. Moving on. Next, now we are going to use critical values because now the problem wants us to find the maximum and minimum for this function when t is greater than 0. So a hint here, similar to what we talked about on the last problem, because the last one we had that interval of 0 to 2 pi, on this problem we don't have an interval, we just have greater than 0. So that means that we are going to have an infinite amount of locations, so we need to think about how do I represent that using my notation. Think about when we did domain for the tangent function or the secant or the cosecant or the cotangent function, stuff like that, or where we found general solutions for trig functions back in, what was that, Unit 3, first semester. So again, you're going to try this on your own. I believe in you. You can do this. You're going to be great. Pause the video, find the maximum and the minimum for this function. Unpause when you are ready to check. Okay, so this one, we got a lot going on here. Let's first talk about the answers, and then we'll talk about how do we get them. So first, the minimum of f of x is 0. The maximum of f of x is 2. The minimum is going to occur at every t equals 333.75 plus 365n, where n is integers, specifically positive integers because we want to be greater than 0. And then the max of 2 is going to occur at every t equals 516.25 plus 365n, again, where n is positive integers. So now how do we come up with that? Well, we used calculus here. So first thing, we need to find our critical values. So I did the derivative. Here with the derivative, again, we need to do the chain rule. So derivative of 1 is 0, so I can kind of ignore that. Derivative of sine is cosine, and then of the thing, right? And then times the derivative of the thing. Well, the derivative of 2 pi times the quantity t minus 60 over 365 is 2 pi over 365. So that's my derivative. Now to find my critical values, I set that equal to 0. Here, again, this is just going to divide out. So really, I'm thinking about where does the cosine of 2 pi times t minus 60 over 365 equal 0. Then I want to think about, okay, well, where does cosine equal 0? Cosine is going to equal 0 at every pi halves plus pi n when n is greater than 0. Again, I'm only including this part because we want t to be positive. If we didn't care about t being positive, I don't need n to be positive either. So then I want to solve this for t. And so to do that, I multiplied by 365, divided by 2 pi, and then added 60. So I ended up with t equals 365 over 4 plus 60 plus 365n over 2. Now I made an increasing-decreasing chart so I can do a first derivative test to see where do I have maximums and minimums. Now also keep in mind, as you're doing this, you should be thinking about the sine function, right? The original function here was sine, so I want to think about that from a graphical standpoint. I know that this had a vertical shift up 1, the amplitude here is 1, and I can think about the period is 2 pi over 365, so the period is 365. So those are things that can kind of help me make sure that what I'm doing is making sense in terms of maximums and minimums. There's no dampening or anything going on in this function, so it's just going to be a straight sine periodic function. So I know once I find where a maximum is and a minimum, those are going to repeat to be the same maximum and minimum at whatever the interval is. Okay, so here's my increasing decreasing chart. I used a lower bound of when n is 0 because I know that I want it to be greater than 0, or I want t to be greater than 0, sorry. So when n is 0, t ends up being 151.25. So then I went to when n is 1, n is 2, n is 3, n is 4, n is 5, just to use a few of the critical values so I can see that pattern of maximums and minimums that I was talking about. Here are the values that come out when n is 1, 2, 3, 4, and 5. Just to be clear, I'm getting that by using this equation here. So I'm literally just typing that into a calculator. And then I plugged in numbers within those intervals and tested to see, do I get positive or negative? Here I got negative, then positive, then negative, then positive, then negative. So I can see that at 333.75 is going to be a relative minimum. At 516.25 is going to be a relative maximum. And then again, that's going to repeat. So here's a relative minimum again. Here's a maximum. This will end up being a minimum, and so on. Don't forget to use your derivative speak to justify your answers. So since f prime of x is less than 0 on 151.25 to 333.75, and f prime of x is greater than 0 on 333.75 to 516.25 at x equals 333.75 is a relative min. And since f prime of x is greater than 0 on 333.75 to 516.25, and f prime of x is less than 0 on 516.25 to 698.75 at x equals 516.25 is a relative max. Now, don't forget to actually answer the question, and the question was, what is the max and the min for that? The min is 0, the max is 2. I get that by plugging those values back in to the original equation. I can also think about it, like I said, from a graphical standpoint. I know what a sine function looks like. This has a vertical shift up 1, amplitude of 1. So from a midline of 1, it's going to go up 1 and down 1, which gets me to 2 and 0. So make sure you're using all of your knowledge. That's why we learn. And it's fun. Okay, next. What angle gives the maximum area? Again, you're going to try this on your own. A couple of hints. Think about that this does need to be a triangle. Think about what you know about triangles. Also think about what should we use as our area equation. I would recommend using 1/2 AB sine C, but do you. So try it, pause the video, unpause when you are ready to check. All right, so what do we end up with? Great question. Theta equals pi halves. That's going to give us a maximum area. What does that mean? It's a right triangle. That makes sense. All right, so let's see how we got to that though. So I talked about using area equals 1/2 AB sine C, or in this case, 1/2 AB sine theta. Another note to think about, and I tried to kind of hint or allude to this, theta has to be between 0 and pi, not including 0 and not including pi, in order for it to actually be a triangle, right? So those are things we want to think about. In this problem, A and B are both 3, so that makes the problem nice. So 1/2 AB sine theta is 1/2 3 times 3 times sine of theta, which becomes 9/2 sine theta. Now we want to use calculus, so we do the derivative. What's the derivative of 9/2 sine theta? It's 9/2 cosine theta. Set this equal to 0. Find our critical values. The only critical value within the interval that is not specified, but we need to think about, is going to be pi halves. In this case, I did the second derivative test to confirm that that is a maximum. So the second derivative, a double prime, is negative 9/2 sine theta. If I plug in pi halves to this, I get negative 9/2. So therefore it's negative. Using my derivative speak, I justify that since a prime of pi halves equals 0 and a double prime of pi halves is less than 0, at theta equals pi halves gives us a maximum area. Notice that it asked what angle gives us the maximum area. It did not ask us for the maximum area. If it asked us for the maximum area, we would have plugged theta back into our equation here and calculated the area, but it didn't. Questions? Great, pretty straightforward. All right, so conclusion. Trig applications are fun. Trig derivatives applications specifically. Now that's not what I have written here, but that's definitely something we want to conclude, right? That's the unwritten, we all know it's true. But also don't lose focus about what we're doing. So we've talked about this before, that we get to the point where we do all of these derivatives, and finding derivatives is great. It's a lot of fun. We get to use all these different techniques and tools that we have, but don't lose focus on what is it actually representing. And whenever we're finding a derivative, that is representing the slope of a tangent line.